Hello, welcome to my channel. And in this video, we want to evaluate the limit of this function. So you have the limit as x tends to infinity of 1 over x raised to the power of 1 over x. Good. So you notice that as x tends to infinity, 1 over x tends to 0 from the right, okay? And raise it to power, the same thing. So it's going to be 0 raised to the power 0 situation, which is an indeterminate form, okay? So because of that, we're going to look at this limit, evaluate it in some way. Good. So I will start by saying, I'm going to make a substitution. I'm going to assign this to something. A sub x be 1 over x raised to the power of 1 over x. Good. So I call the function a sub x, okay, more like a sequence kind of notation. And then that simply means we're going to be talking about, that means we want to find the limit as x tends to infinity of a sub x, because a sub x is now the function we're looking at. Good. Great. And now, but notice if a sub x is 1 over x raised to the power 1 over x, that simply means if we take the ln of both sides, we're going to have ln of a sub x to be 1 over x times the ln of 1 over x. Good. Okay, just by pushing the power to the front and taking the logarithm of the base in this case. Okay. Good. But notice that I can rewrite this 1 over x as ln of 1 over x divided by x, alright? But let's just look at taking the limit of both sides as x tends to infinity. So we're going to have the limit as x tends to infinity of ln of a sub x to be the limit as x tends to infinity of this term at the top, then we divide that by x. Just from our previous discussion, that we can put this 1 over x, the bottom. Good, great. And then from there, we would like to look at, okay, so from here, we would like to see that as x tends to infinity, ln of, now 1 over x, as x tends to infinity, 1 over x will tend to 0 from the right, okay, just like when we had over there. Ln of 0 plus, that is, we are approaching 0 from the right, the logarithmic function will be approaching negative infinity. So this will be negative infinity, approaching negative infinity. And then as x tends to infinity, of course, x tends to infinity, that will be in infinity over infinity form, okay, which is also an indeterminate form. So we can't just arrive there. But the good part here is that when we have infinity over infinity form, okay, an indeterminate form, we can make use of a very powerful tool, which is called the L'Hopital's rule. Good. By the L'Hopital's rule, we talk about that this limit will be the same thing as the limit as x tends to infinity of the derivative with respect to x of the numerator divided by the derivative with respect to x of the denominator. So we just differentiate top and bottom and then look at the limit again as x tends to infinity, or by maybe substitution. Good. Okay. So if we differentiate the numerator, notice this is a function of a function. In the logarithmic function first, we're going to differentiate that. When we differentiate logarithm of something, it will be 1 over that thing. Okay. In this case, it's going to be 1 over x, which will just give us x. And by chain rule, because this is a function of a function, we differentiate the outside function with respect to the inside, or in terms of the inside, and then we now multiply with the derivative of the inside. So you differentiate 1 over x, you're going to have negative 1 over x squared. We multiply this with negative 1 over x squared. You can check this out by just writing this as a power function x to the power minus 1, and then you apply the power rule on that. Good. Then we divide this by the derivative of the denominator. It's just going to give us 1. Great. And then maybe we can look at the numerator a little bit, look at the limit as x tends to infinity of, well, when we multiply x with negative 1 over x squared, we're going to have negative 1 over x at the top there, and the denominator is just 1, so maybe just keep the 1 like that. Good. So you notice that as x tends to infinity, this denominator is getting larger and larger, greater than any real number you can compare it with. That means the fraction will be breaking down to 0. And since we're having minus here, maybe it will just be like 0 from the left, which still means that the limit is equal to 0. But this limit is not just the original limit we want to find. Take note, we want to find the limit of a sub x as x tends to infinity. But the limit we just sought for is the limit of ln of a sub x. So we should try to recover a sub x from this ln. That's just by using some sort of exponential function. So let's define an exponential function and maybe take the exponent of both sides. So I'm going to draw a conclusion here. I'll say that the limit of this, right, ln of a sub x as x tends to infinity. Of course, we notice that that is equal to 0. If we make e the best of both sides, that would mean e raised to the power of that limit to be e raised to the power of 0, because the limit is just 0. Good. Since the exponential function is continuous for all x in R, and in fact for all x approaching infinity, that simply tells us that we can rewrite this as the limit as x tends to infinity of, we kind of push this inside, that will be e raised to the power of ln of a sub x, which will be e raised to the power of 0 is just going to be 1. Good. So you notice, since this exponential function and the natural logarithmic function are inverses of each other, then their composition will produce the identity, which means we're going to have this will produce the limit as x tends to infinity of a sub x, which is equal to 1. And in fact, this right here is the required limit, and that is it. Okay, great. All right. Thanks for watching. Please subscribe to my channel.